Here we have a high amount of 4K textures, which has a quite high bandwidth cost, around 2.6 gigabytes as highlighted there. Setting to low, we can save a lot on that texture bandwidth. This is quite an obvious optimization you can do. Obviously, you encounter some visual degradation, but this is one of those things to keep an eye on, not to forget to use the highest level quality asset that you have and use lower textures, especially if your objects are far away. You can very often get away with much smaller texture sizes. I'll first do a quick overview of what I'll go through, and then I'll move into more detail in the following slides. We'll very quickly talk about principal materials, PBR materials, how they work, and some small optimizations we can do there. Then I'll look into shading optimizations, that is custom materials in Qt Quick, and things to look out for in shader code. Then I'll briefly mention shader precision, and then move on to textures and their size and compression. Starting off with principal materials, they are pretty much universally used model these days. The models slightly vary depending on your render engine. For example, we have Lambert, Burley, and Horizon are available to us, and they're very impressive and work especially well on hard body surfaces such as cars, as in this example. And it allows us to use the material in multiple lighting conditions and multiple environments, and still looks correct since it's using that physically based rendering, as the name suggests. Keep in mind that they do have a computation on texture read cost. They do have a lot of properties that you can potentially use and a lot of texture usage. That being said, most new hardware, arguably even embedded, is powerful enough to handle PBR. And I have rarely found it to be a bottleneck these days. However, if you are experiencing issues and noticing high fragment shader usage in PBR shaders, it might be worth playing around with some properties. Sometimes it might even be worth cobbling together a custom shader that mimics the wanted visuals and see how that impacts performance. There also may be some sort of sneaky performance caveats with some of these properties. I've highlighted transmission as one. It is a nice effect and gives your translucent objects a nice realistic look, but in Qt Quick, it does perform an extra render pass to create the intended effect. So profile and keep a lookout for these effects. Moving on to custom materials and custom shaders, one of the most common bottlenecks to run into these days is texture read bandwidth. So as in this example here, GPUs will stall waiting for texture fetch operations. Now, GPUs can execute another warp when one has stalled to sort of allow you to do useful computation while waiting. But if you have a lot of stalls, that will still cause a lot of slowness. And if you notice that texture reads are causing stalls, there are a couple of things that you could look out for. The first thing is to consider packing your grayscale textures into one. In general, it's cheaper to read 4 channel textures versus 4 1-channel textures, since this results in only 1 texture call rather than 4. So in this example, which is a common PBR example, is to, rather than individually sample your metalness, roughness, ambient occlusion, opacity from separate maps, you can use 1 texture call to get 4 channels and then distribute those accordingly. There's a good blog post on the matter by Charles Grassi. Another source of slowness can be random texture sampling, as seen in this first picture. GPU sample data in cache lines, which allows the GPU to use 1 read for multiple threads potentially. So say you have 8 threads and you have a cache line of 8, then you get 1 read instead of 8 reads, so an 8 times faster read. However, if you're reading random texture coordinates, that will cause cache misses, and in the worst case, you'll have to do all those 8 reads anyway. So keep in mind that random texture sampling will have a performance cost. Texture-dependent reads, which are used in flow maps and parallax, for example, can also cause slowness. So GPUs, as mentioned earlier, do work in warps or wavefronts. And when one warp stalls, the GPU attempts to get another warp to take over to still do useful work. This is generally called occupancy, which you want to keep as high as possible. But in this case, if we have a texture-dependent read where one texture relies on another texture to be read, we can't do that meaningful work because we require that data. For some effects, we can't avoid this and sort of just have to accept the performance hit. So this is not something that you should necessarily never do, but it is something to look out for. Sometimes you can pre-compute texture coordinates you need in the shader. Then sometimes we can move shader code that was executing on the fragment shader to the vertex shader. So in this case, we actually have a real world example of code that I found that I moved to the vertex shader, which was computing the data for parallax offsets. We can do this computation on the vertex shader instead and pass the variables out as interpolated data using the vertex post-processing step. And in this case, the underlying geometry was a flat plane. So instead of doing this for a large amount of pixels, we can do it per vertex, meaning 4 times. So we effectively eliminate a lot of unnecessary computation. Yeah, be vigilant for code that you can execute on vertex shaders instead of fragment shaders. Then moving on to shader precision. In this case, we mean the size of the variables, that is your floats, your integers, in registers. And it is possible to go from 32-bit integers to 16 bits. The register pool is divided among shader threads, so lowering register usage can increase the amount of active threads that you can run at a time. Now, precision and depth calculations usually need high precision, but lowering the precision can be useful on mobile platforms where some operations don't need as high shader precision. And it is one of those things that AMD, for example, recommends. And in GLSL, you can implement that with the precision medium P or precision low P specifier. In HLSL, it's slightly different. It uses the min16, and I believe this also ensures that if your device wants to use higher precision, it will convert those into higher precision. And in QtQuick 3D, you can enable that with the QtQuick 3D medium precision or QtQuick 3D low precision environment variable, which you can pass either in, say, your main.cpp with the qput-env function, or just put that in your environment variables directly. Right, and finally we get to textures. Just a quick video first. Here we have a high amount of 4K textures, which has a quite high bandwidth cost, around 2.6 gigabytes as highlighted there. Setting to low, we can save a lot on that texture bandwidth. This is quite an obvious optimization you can do. Obviously, you encounter some visual degradation, but this is one of those things to keep an eye on, not to forget to use the highest level quality asset that you have and use lower textures, especially if your objects are far away. You can very often get away with much smaller texture sizes. It's also worth mentioning that Mipmapping is a visual improvement as well as an optimization. Mipmapping refers to internally creating lower resolution versions of textures to be used when you're further away or when the texture is viewed from a sharp angle in the case of anisotropic filtering. And it improves visuals by removing flickering that you would get due to sampling errors. But it can actually also be a performance optimization, as it can reduce those cache misses that I mentioned earlier, as there are less possible samples as the texture size gets smaller. Then quickly about compression. Block compression has been a standard these days. So this is compressing textures into blocks of pixels, usually about 4x4. So in the case of, for example, the BC1 compression, we can reach compression rates of 1 to 8, although there may be some visual degradation. And for example, BC1 only works optimally with RGB rather than RGBA. But there is also a new compression format called ASTC these days, which attempts to sort of supersede the prior compression formats. So I would really recommend looking into compressing your textures into ASTC textures and see how that impacts your texture bandwidth.